Let's begin. Hey, hello, and welcome back. I am back to doing some coding today. Again, relaxing, and I'll be sticking with the idea that I'll be working on game of life. So in the last episode, I wrote a game of life, and by the end of the episode, it worked. I can pass it in any rules. So not only game of life rules, but there are other kinds of lifelike games, game rules, and it should work. It worked. And in this episode, I want to visualize. I want to have a better visualization of the game of life stuff. So let me check my YouTube stuff. That's all right. Which YouTube's working? Good, good, good. Wrong Firefox. Okay. And OBS controllers are here. I think we can get started right now. So if you've not known, the repository is here. Oh, cool. I can do that. github.com/chewxy/ll. You can follow along. Yeah, so there was nothing much that changed since the last episode. I fixed a bug in the tensor library, which now makes it work. So let's get started. Turn this off and goes to 2. Goes to 2. All right, here it is. We've got the world. In the world, there is basically a world. This is the accessor of the world. It helps with accessing this dense tensor as a slice of floats. And this is the processing part of the world. And let me move this around, move this up here. So a world, it contains a rule, and it has a board, and this is the accessors, and then there's a backup board in order to do fast processing. Now you don't have to have this backup board to do fast processing. I just happen to use this board because I did something, which is to say, yes, I sliced. I take a board and I take a slice of it, and then I compute, and then I update the originals. So you can't do that if you have one board. So let me go to the explainer and explain that to you. So if I have got one board like that, and I take a slice, let's say I take this slice, and then I compute whether for this state, for example, right? Whether this is alive or not. Then if I mutate this, let's say this is 1, now this is 0, then this slice would now be wrong for the computation of this node, this cell. So in order to use slices, I need to make a copy. Now, whether or not this is the best way forwards is not necessarily, I don't have necessarily the best idea whether this is the best way forwards, but it is a very, very useful way. I mean, memory is fairly cheap. I can have a very, 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 very large world in this board, and it still works. So another weird bit that I did was that I made it a float. I think down the road I will explain why I chose a float. Because I have some interesting ideas on this lifelike things to do that requires floats. But usually you would use something smaller, a data type that is much smaller. Say, you can pack this into bits, for example. If you really want to make it really efficient, and that's what a lot of efficient, like Golly, for example, it's probably doing that. So let's see what this main program does. All right, so this main program creates a 9x9 board, and does 1357 rule 1357, which says that if you count a grid of 9 cells, and then for the okay, so let me just go back to the explainer. So this 1357 rule, so it's B1357, S1357. So you've got many tiles, many cells, And what you do is you take a slice of this cell, and you look at 9 at a time. So for this, when you want to analyze this, the one with X, you look at 9 the 8 cells around it, or the also known as the Moore neighborhood. There are different neighborhoods for different for different whatchamacallit. Sorry, I need to send this link to someone. Someone's just asking for a link of this video. So right, back to the OBS controller, and right, yeah. So if you want to analyze this cell, you need to look at 8 neighbors around it, and this is called the Moore neighborhood. Right. In the last episode, I talked about other kinds of neighborhoods, like Manhattan neighborhood, where you only consider the 4 neighbors around it. If you're analyzing this cell, 1, 2, 3, 4 neighbors around it, which is this, and this. That's a different type of rule structure. But the reason why I chose this rule structure is that you can actually oh, okay, fine. You can't, but again, right. So this representation of rules is not as flexible as I would like it to be. There's another more flexible one, which is the Wolfram code. I will come back to that, but for now, I'm only dealing with something called isotropic game of lives, meaning that I only care about the sum total of neighbors that are alive or dead. There are rule sets that require not only the sum of neighborhoods, but specific locations of the neighborhood in reference to the cell itself. I'll be talking about those. I'll be building those much later. But for now, we'll just stick with the isotropic rules because we can already see quite interesting things happening with the isotropic rule. So go run may start.go. So if you can see this, basically what we'll do is we will this is the initial game board, a 9x9 game board, and only one cell is alive. After this, after the first iteration, this many cells are alive, and then after which they sort of disappear, and you're left with 3 cells that are alive, and then each of these 3 cells become again a cube, and they sort of move like that. See, this original is still alive again, and this and this one. In the last episode, I mistakenly called this the glider. I was half asleep, to be honest. It's about 11 p.m. back then. But this is actually called the replicator. By it's the rule set replicator. So if I change this to B23 and S3, basically a cell is born if there are exactly 2 neighbors, or 2 or 3 neighbors that are alive, and it only stays alive if there is 3 neighbors. So let me just go to glider, search for the pattern that that is actually a glider. Actually, no. Let's do this. So the cross is actually a pattern in the game of life. So if you set 2 together, it will blink out into 2. So 1 1, and we will set another one as CV 2 2 0 1, I believe. And let's just do this for 5 iterations. So you see here now, this is 1 1. Nope. Yep, this is 1 1 2 1. So this will die. Maybe not. Okay. So the point is there are many like things you can draw on, and then you can see it go live, alive or dead. But this points out that it works. 2-1. 2-1. Okay, let's see what happens when I go to 2-1. Okay, let's do 3-1 as well. So this one is basically setting the value, and these two are the coordinates, XY coordinates, right? Yeah, yeah. So this is supposed to be a early brace. Of course. Still dead. Okay. There's a bit of a bug here. So if I know this correctly, this should become a vertical line, but it's not becoming a vertical line. Instead, it's got 101, which is not correct. All right. So what we can do to analyze this thing is to switch to a much smaller board, and now we can do this. 1-1 would be the middle, so 0-1, 0-1, 1-1, and 2-1. So now we can watch a smaller board, and with the smaller board we can write some. Okay. Right, now we can don't need to see this anymore. Just need to see the first and last. Okay. All right. So how do we debug this? All right, what we can do is we can look at the sum. Ah. Yes, the pattern is supposed to persist. So Jeremy asked if the pattern is supposed to persist. The pattern is supposed to persist. Okay. Oh yeah. I might as well do this. J. And now we can just pull down this into 2 iterations. In fact, 1 iteration is more than enough, but I just want to see what happens there. Okay, good. So I1, J1. I1, J1 would be 0, 0. I1, J2. So let's look at this. Let's print, not the rule, but let's print the world itself. Cool. Now with the world in mind, we can see what's happening. I1, J1 would be 0, 0. Because I and J are a much bigger board, and this much bigger board will come in handy in the in what I'm about to do next. This whole point of this video is for you to do that. Anyway, so let's just see if I can find the bug now. If I can't find the bug now, I will fix the. I will work on the other issues, topological issues first. And speaking of topology. By the way, if anyone's watching, this is one of my favorite topology books. It's called The Shape of Space by Jeffrey Weeks, and it's quite fun to read. It's a very good topology book. So yeah, you should check it out. Anyway, back to this. I'll talk about topology a bit more, and it's a bit mind-blowy. Yeah. So 0, 0 will be 2. Yes, there'll be 1 and 2. Yes. 1, 2. The sum will be 3. Yes. Swap these lines and also print S because I cannot do arithmetics right now in my head. It's late. It's 9 p.m. I am baited a long time ago, so just want to relax, man. Oh yes, I forgot. B23 and B3. Yep. So there is a notion of outer isotropic and isotropic. When it's written B23, it is outer. So there's outer isotropic, so you need to minus the sum of, let's say this cell is being analyzed, right? So you sum all the cells up. It's 3 minus 1, that's 2. Or that survives that. So there is so S here is the sum. Let's say we are analyzing this cell. S is the sum and of this slice, and that's 3, and then minus 1, that will be 2, so it will not survive. So that's called the outer isotropic. So you analyze everything except itself, and then there's the totally isotropic, which is you analyze everything including itself to count into the option. So this allows for more config options, which is what I want to talk about. Anyway, so by default, it is not outer isotropic. So we can do this, right? We can go to the step function and do this. If well dot is s minus equals to int of what was it, b? Was it b? Yeah, okay, b. If world dot is outer isotropic, then you minus it as int of minus int of b I j. There you go. Now, if you look at this now, by default, the world is no longer isotropic, and we're now running by the game of life rules, B23, S3. Yeah, okay, sure. See, it sort of flickers from vertical to horizontal to vertical to horizontal. So this is a matter of isotropy. Yeah, that's what it does. So now I've verified that the game of life works. Let's see whether this one, or the original one, works as well. So if it's not outer tropic, it will not. Oh, yeah, the rule is 1357. I forgot. I have to change the rule as well. So the 1357 rule is a outer isotropic rule, whereas this is the game of life itself is a totally isotropic rule. Okay, good to know. Like I said, I know most of these things, like from a theoretical point of view. I've never actually implemented the game of life until last week. Yeah, and so I guess I have a different viewpoint to most people. Sorry. Yeah. Okay. Um, right. Now I want to talk about the world itself, right? The world is right now a flat plane. So once it moves away, once a pattern moves out of the plane, it's dead. It's not considered anymore. So what happens if we want to have different topologies of the world? So imagine the world is a piece of paper, right? Which is easy to imagine. Here's a bill. Imagine the world is a piece of paper. You can draw a grid on it, and then you can roll up the grid, right? So you can have such that it connects to one another, right? Does that make sense? So then you've got a cylinder as a world. Basically you've got a cylinder as a world. Here's an example. A cylinder as a world. Imagine a grid on this. So your patterns moves out, but it comes back on top. However, these ends are not connected, right? So these ends are not connected. So if it moves out and to the right, only a portion will come back on this end, on this end, on the top end, right? If you want it to come back on the top end and top left, then you need to have these things connected, like these two ends connected, like a donut, a torus, um, and that's how Pac-Man, the Pac-Man world is. The Pac-Man lives on a donut. Asteroids live in a donut. I don't think anyone here who watches YouTube is old enough to know what asteroids is. So anyway, so let's rename this to T, and let's rename this to A, because T represents the topology that it's in the grid. Okay, let's rename this to G. There you go. You rename this to G, and then that's it. The grid that it lives in. Now, what type of topology it is? So I've added a config in which there's a topology. So type topology, and this is basically an enum. Right? So the default topology would be a plane. And the second that one would be a torus. Now, I've considered taking this plane and I was thinking about this in the shower before I decided to stream, that there are ways that you can talk about topology. So you can talk about curvature, for example. Yeah, a Möbius strip is a cylinder, essentially, more or less. Yeah, a Möbius strip is a cylinder. So Jeremy asks that says that the default should be a Möbius strip. You guys know what Möbius strip is. Möbius strip is a strip with a strip of paper that's essentially unending. Let me see if I've got spare paper to draw. Anyway, I think everyone knows what a Möbius strip is. So we're not building maybe a strip and a cylinder have essentially the same topology, more or less. One is oriented, one's not oriented. So there are many sort of dimensions to topology. Curvature is one of them. So one of the things I was thinking about was maybe we should make a topology of different curvatures. Like if you've got a plane, you can curve it up into a positive curvature or negative curvature. Then you have a sphere or a hyperbolic space, a hyperbolic plane in which you can do your things. But then I thought that's a bit too complicated. So I'm just going to stick to these three. Yeah, and here we have the different types of topology. So with regards to a cylinder, there's a cylinder H and cylinder B. So what cylinder H is basically, it's connected by the horizontal axis. So if a pattern goes out of the right, it'll come back to the left. Whereas cylinder V would be vertical, and torus would be, you know, both H and V at the same time. Very, very simple. And to what you want to call it? Yeah. Okay. So the step function is very simple, right? You just switch on the topology here and then make a copy. That's it. So you got case plane, case cylinder H, case cylinder Y, V, case torus. Again, if you're looking for a good topology book to brush up on topology, I highly recommend The Shape of Space. Very good. And I'm not related to Jeffrey Weeks, so yeah. So on a plane you do nothing. Very simple. On a cylinder H, you basically copy the left into the right and right into the left. So if you're not aware of what the design actually is, sorry, that was my keyboard on my tablet. Anyway, yeah, okay. So the design of the buffer is that you've got, the buffer is essentially a padded the buffer is essentially the world but padded by one. Okay, so this is the buffer, the outside bit. This is the buffer, and this I'm going to highlight as, I've got a highlighter. Why don't I use a highlighter? This is a buffer, and this is the world itself. The bit the bit that's being highlighted is the world itself, right? And so what you do for cylinder H is you copy this into here, this side, and you copy this into here. That way you can essentially do the same thing. Oops, sorry, drawing is not on screen. Let me try this again, because I'm not used to doing this. Anyway, so let's do this again. So this is the world. It's a 4x4 grid. Okay, 4x4. Right? And this is the buffer. The buffer is essentially the same thing, but one padded across everywhere. Okay? Now I'm going to highlight the world. This is the world, and everything outside of this highlighted line is the buffer. So to change topologies in the three examples I do is very simple. For example of cylinder H horizontal, if a cell were to go out this way, well, what we do is we take this side and copy it into here. into the buffer. And we take this side and copy it here. This way, when we take a slice, let me use a marker. When we take a slice, for example, here, you're automatically analyzing the values from here. Does that make sense? Yeah. So and the other one, the cylinder V would be the opposite. You just do it vertically, and torus you do it for both vertically and horizontally. Simple. All right. Let's move this back into. Let's change this back into a ballpoint. Cool. Now let's go back to coding. Like I say, it's just a very few lines of code to change topology. Yeah. So with the drawing in mind, let's work on cylinder H first. So w.buff, that would be the rows. Sorry, or I range w.buff. Okay. Then I need to copy the last thing of the world, right? So w.buff I0 equals to w.buff I then okay then w.buff I minus 2. Yes, that is correct. So it just copies. Yep. Yep, makes sense. And for I, oh, this is easier, right? So w.buff 0 equals to, okay, we don't do this. Copy w.buff this is wrong. That's 2. That's it. And for us, we just copy both. What? I'm going to show you guys a bit of a naughty, a less well-known, a less well-known, a less well-known Go case, a less well-known Go syntax. So, through. There you go. At default. I can't spell. Okay. I don't think this works. Can't fall through here. Yeah, you can't fall through here, right? Because it's in an if statement. better yet, you can do this. This is very just break out of the case and fall through. See if this works. Default conflict, what the heck? When was that imported? I did not import it and import that. Yes, not w.buff. w.b. I keep forgetting what I call this. So yeah, probably rename buff to something else. What's this? Oh yeah, okay. What are we on? We're on 2.3, so we need to CV 1.0.1 CV. Okay, it works. Now let's see what happens if I change the world's topology. Oh no, it doesn't matter, right? Okay, so I know we shift it from 0.1 to 0.2. See? Now if we do if we set w dot topology equals to cylinder v vertical, now we should see something different. Yep. So you start here, and then you, instead of just going down and dying and just leaving 2, it comes back up on top. And that's not correct. Oh yeah, I forgot. So before that, yes. You need to actually zero out the buffer area first. So not that difficult. w.buff.0. That's still not quite correct, is it? Did I get saved? All right, so one other thing that we can do is to actually look at the buffer. Instead of looking at G, we can look at buff. There you go, that explains a lot. Now if you look at the buffer, instead of zeroing it out and entirely, it just copies the top. So it copies this to the top. So this grid over here is the 9 cells that we're interested in, and copies the bottom bit to the top. And this is of course to aid in the analysis of things. So there you go. You have when you analyze this cell, you've got one cell. Oh, right. You have to copy both left and right. So I only copied right and left. I didn't copy left and right. So yeah. Where is it? Okay, and copy w.b minus 1 from w.b1. There you go. Aha. Okay, so now we know that it works. We can verify this and run this again. What the hell? What? So in this version, it's correct. Yes. All right. So when you analyze this, you've got this, which is 3. So this goes alive. Ah, that's interesting. So, yes, this is correct. Surprisingly, this is correct. Now, this is very interesting. So it's not that it's just moving, it's actually considering it's making a copy of oh, you can't see my hands moving on the screen. That's crap. So this is a copy of this this. So basically, if you are considering this cell, then the cell above it is technically this cell in the world. So this analysis turns out to be quite correct, and it will end up with all ones, which is very interesting. That means in a cylindrical game of life in a very small grid, it will die and essentially become a barren world. What do you know? Okay, so I did this on the V. I need to do the V. Right. Yes. Copy this and w.b I w.b 1 equals to w.b I 0. No, 1. Okay. So let's hang on. Let's run this as cylinder H. Hey, it's moving. Now, instead of printing w.g, let's print the buff and see if we can understand what the hell's going on. Yes. Yes. Aha. Now, this is very interesting. Now we've got a pattern that actually scan lines down the grid. That is very, very interesting. Okay. I'm my preliminary analysis says that all these are correct. It's not your usual game of life that you see, because most game of life that you see that does repeats upwards does just moves the cells upwards without actually analyzing the world as a whole. Yep, okay, Taurus makes sense. Got it. All good. All right. Now, the next thing I want to do is to make a UI for this. And to do that, let me save this. What's the diff in my go mod? What? Yeah. Okay, yeah. What? When did I import these things? Okay, sure. I'm not sure if I did actually import that already. I don't stage come in. Okay, I'm just changing names to package LL, and I'm going to turn this around, and we're going this the package would now be just basically um containing the world and the rules of the game, whereas we'll create a new package called UI or render, I guess. Now there are two types of render, right? So you've got ASCII and you've got game. So visual render. So viz.go. Cool. Viz, and we're gonna move LL into CMD slash ASCII. Okay. CMD slash ASCII L slash main.go. Yes. Why am I making the buffer only? Okay. Anyway, yes, to make it. This stupid pop-ups suck. Okay, I'm gonna have to change my Go mod. And now I'm going to have to change this. Right, so rename this to new. And now when we create the world, we just put all these options in. I'll probably transform them into some sort of config struct, but it's not necessary right now. When you're just starting out, right, with a program, don't make things too complicated. And then what else do you have? There you go. And then we can move this main to here. Ugh. Anyway, so so right there. Now I've got this. I can organize imports, I think. Oh, nope. Anyway, changes need to be saved. Import. And this is now wrong because now we need to set topology. Topology would be a torus by default, no, plane by default. That's the one that everyone understands. False. That won't work. Of course, that won't work because that's utils.go, and utils.go needs to be called ll. And the go mod file needs to be updated to be called what? Yes, might as well do the redirect nonsense now. What's the redirect syntax again? No mod redirect syntax. Replace, not redirect, replace. Right, replace slash does not exist. What? What the crap? Oh right. I'm not on Mac. This is crazy. I'm not on a Mac. What am I doing? There you go. Very simple. Let's copy this. Why is my mouse lagging? Ah, yes. Of course, I'm missing something. Workspace here. Excellent. Okay. Huh? Main.go 150. Right, yes, of course. This one I forgot to save. Imported and not used. Blah, blah, blah. Yeah, that's frustrating. When your LSP just fails for no reason, and it does happen a lot on this. Jesus, this fly make nonsense. Right. Not CV, but ll.cv. Okay, let's not bother with this FlyMake nonsense because FlyMake can sometimes get a bit noisy. Let's instead focus on the game bits on a UI because that's more fun. So let's do that. So pkg.dev/github.com/hajime Hoshi/abby10. There is a v2, but I'm not particularly familiar with v2 of abby10. But I'm looking for type game. There you go. Type game is nope. Right, let's see what. Yes, it's an interface. That's the one I'm familiar with. Yes. Okay. So, quite simply, what we need to do is we need to make this into a game. So in the render part, we put this under viz. Okay. Type. And we just, l.world import. That should be correct. Yes or no? Let's see. This new returns new world. So start. Okay, now there's also layout, I think. How do I do this? Layout. Layout. Hey. No. Layout. Let's just search for layout. There you go. What's this? There you go. Interface requires layout. So func g layout outside width. Int gets you the screen width. Screen height. Now there is a program called Josharian actually has a program called or Impel, which automatically generates the interfaces for you. You just have to point it which interface to generate, and it will generate it for you. And I had it at one point in my Emacs, and it's just a button, and it just generates all of these nonsensical stuff. But when I moved to LSPs, it sort of failed to work. No idea why. And let's see. So what should we do? I'm not going to compute things, so I'm just going to return so let's just say we do an 800 by 800 screen or something. We'll come back to computing the actual like screen size, but yeah. I will handle that a bit later. What else is required? Update. Okay. Oh yes, I remember now. So I'm fairly familiar with Abitan because I wrote a couple of games in Abitan for myself. In the past. Maybe one day we will see light of those, but wait, this is annoying. There you go. Suddenly it works, and sometimes it works, sometimes it doesn't work, and that really frustrates me. Yeah. Anyway. Right. We need to have an update. Oh, we also need a draw. Func draw. Because so the draw. There you go. So one thing that Abitan does very well is it separates the game loop, which is what update does, and the draw loop. In a game of life, there is no difference, right? You update and draw at the same time because it is honestly it's a very easy, very simple, straightforward thing. So yeah. The only time you want an update would be when you press a button, right? Otherwise, you just it. This is a playerless game. It just runs every instance. You just update the drawing. That's pretty much it. Uh, you know what? I'm actually thinking we might actually allow for a button to be pressed. Yeah, sure. Why not? Uh, so the game loop has what's this, button press, mouse button press is mouse. Yes, mouse button press. That's the one I'm looking for. Yep. Mouse button. Okay, cool. If mb10 dot is mouse button pressed, and the mouse button would be left button. It will be mouse left button. Mouse button. Mouse button left. That's the one. And then with that, I can actually grab the cursor position, which is position. Touch. There's touch position. Cursor position. There you go. Brilliant. My memory is not that bad. Hey. And then we'll do something about XY. Dot do XY, which the to do of basically figure out where in the board is the thing being drawn. So how big I want a cell to be represented is interesting. So how do I do that? You can make the cell big, and oh, you can scale it. Of course you scale it. Duh. And return nil. That makes sense. Okay. All right. So there are some chats I see. Okay. Anyway, Jeremy says button presses would be cool. All right. Thank you, Jeremy. I heard you. I also think that button presses would be cool. So yeah. So how do we draw? You have to draw for each cell, and each cell has to be a square, a rectangle. Sorry, thinking. Okay, right. You need to draw the world. So I was wrong. I actually did need this to be exported after all. So earlier in this episode I renamed this to small letter a. Well, it turns out that I was right. You need to actually yes, and Darrow says palette tree, which is a new 3D printer thing. Anyway. Yes. Okay, so what do I draw? What do I draw? For I range G dot A, because G dot A is embedded inside. G dot A is from here. For J range G dot A I. What's the draw thing? Is there draw rectangle? Right. Draw rect shader. That's a shader? Oh, this API is experimental. I just want to draw rectangles, man. Is there a utilities? Yeah. So that's interesting. Yes. Oh, that's nice. I can see everything here. Run game. Very good. Very good. Image. Image. Place pixels. There you go. Abitan util. Ha. Oh, yes. There you go. Brilliant. You can just draw a rectangle. That's what I remember. You can just draw a rectangle. Abitan is amazing, by the way. You guys should just use Abitan. Even this is not a game, right? But you can still do Abitan stuff. You can use Abitan as a display thing, which is freaking amazing. Okay. Oh, and conveniently enough, it requires everything in float. Yes. Color.color. Right. So the destination Abitan util dot draw rect screen. X and Y would be I and J, so that would be float 64, I, float 64, J, crap. I need to figure out the scale shit. Okay, I know. Times G dot scale. Times G dot scale. Oh, you need two scales, right? Yeah, you need two scales. Scale H and scale. So if I assume that the board is a square, then I only need one scale. Otherwise, I need to scale twice. So I would be rho, so I need to multiply H. This would be W. And width would be scale W. And height would be scale H times basically times 1. The color, if it's 0, then it's color. C. Okay. Very simple. Color black is dead, white is alive. If G dot A I J equals to 0, equals to 1, then the color is very simple, right? What's color? Color dot please work. It's not working. Okay. This is very annoying. Okay, now what's this? Image, nope. Image color, image color, image color, image color. Nope. That's the command. G would be dot go dot dev slash is that color dot black and white? Yes. Okay, color dot black. White. C equals to C Am I correct in this? Annoying. It failed. Image/color. All right. What do I do with the scale thing? How do I scale this now? I've just put the scale here as ah. Right. Keep forgetting this. Outside. Right. Need to figure out where the layout is. Window size returns the logical. Okay, so let's make this new world and new because in Go the convention is if you don't return a pointer, then you just use the word make. If you return a pointer, use the word new. G and now I want to make Windows. Right. So the scale is very easy to compute. So you take 800 divided by the height of the world, 800 divided by the width of the world, and then you generally have a scaled version. The question is when do you initialize this, right? So so scale h equals to w dot. Let's do this shape. Okay, so would be s 0, that's a height, and 800 divided by s0 and make it a float. Scale w equals to float 64, 800 divided by s1. Again, s1 and s0 would be integers. I'm just making it float 64s. Anyway, const is basic. I'm making this const because it's g.a. Right. Nice imports. Okay, let's see whether Ebiton util was imported. Excellent. Why is it still redlined? I have no idea. Uh, I'll need to step at one point. Okay, step. G.step. The step return an error. Yes, it's return an error. Wow. Okay, is this that should work, right? That's it. Now all I got to do is handle the mouse clicks. Okay, let me check the chats. Anyone chatting, saying something? Nope. Okay, no one's chatting, no one's saying something. Okay, cool, 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 cool. I am lost. I don't remember why I'm doing that. Hmm. Okay, now I have to handle this. Now let's write a function called handle mouse. What do you do when the mouse is clicked? By scale. Uh, Scale h equals to x scale. Yes, that's quite correct. Then you flip. Right? Then you flip the cells. It's alive, it's dead, it's dead, it's alive. A, I, J goes to 0. Dot A, I, J. Let's not do that. So, yeah, case 0, 1.0, and then default heading. So there is a good reason why this is why I'm using a switch. I'm using the switch because, well, I want to look at my cases easily. G dot A I J goes to 1. G dot A I J was 0. That's all right. Yeah. And state and step. Right, now I have to control the game's speed. Right, so we've been doing it every 1 second. Run game, where are you? Hmm. Okay, now let's put this into cmd slash visual main.go. So go mod init main. Yeah. Right. Main. Let's just copy and paste this. What's this? Why is there a FlyMake file? What in the world is happening? What? Anyway, let's just copy this for it. We just make this oh yeah, do that whole nonsense thing again. So we've got a world, and now we want to make it's not go. We want to make viz dot make w into a g, a game. What is happening? Why is my computer lagging? Okay, then what do we do? Right, we run the game. Right, we just run the game. Easy, they say. um yep. 10 dot, what's it called? Per second. Ticks per second. 60 ticks per second. That's 1/60. I'm gonna change this to 1. So is that TPS? Uncapped TPS. TPS. Current TPS. I want something. Max TPS. Nope. Set max TPS. There you go. Set max. 1 frame per second. 1 tick per second. Sure. For now, anyway. Let's go back to the Ableton example. Thank God, this is terrible. Way to the top, there is big bit on top. That's one. This the set window size. Set window size to 800 by 800. This is again hard coded in Ableton.set window title hello live stream if 10.run game continue panic, sure, why don't we panic? Right, let's run this and see what happens. You know what? I know why my computer is lagging so much. It's because of the the LSPs, if I code for a long time, they start lagging and I have to do something funny about it. Ah, yes, of course. Lag. Okay, this is not a joke. Seriously, what's wrong? What's going on? This is crazy. Um, this is ridiculous. I do not like. Yep. This is crazy. Seriously. Nice. How long have I been going for? What? Oh, render slash viz. Okay. Right. Render slash. Okay, what's happening here? Fail. Okay, so this fails to run. Um, but it fails to run mainly because of some other things actually. So I'm actually now looking at this from a terminal point of view. Visual. Yep. Um, I don't have the graphics card related required nonsense. What? I have no idea what's happening, so let me just Google this for a bit outside of the hell. So, hmm, locate libgl. Oh, fucking hell, I got so many GLs. So, a bit of context. I'm working with Mark Kramer to actually allow for Vulkan to allow for Gogonia's tensors to run on Vulkan. And so as a result, I have all sorts of weird OpenGL shit that I have no idea what I'm doing. But hey, I found this issue. This issue. All right, so I'm gonna call this a night. I've been doing this for a bit. It should work. I've been online for 1.5 hours, and it should work. So this is Hajime Hoshi's issue. That there's this thing, right? It fails to build correctly. I will figure out the rest. I have as many libgl nonsense. But yes, I will figure out the rest. All right, so I think I'll call it a night. I have a good feeling that I pretty much got this correct. But once I figure out the linking thing, I should be able to just run it. Yeah. Until next time, just follow me on Twitter at CHEWXY. And thank you. Thank you for joining me. I had quite a fun time figuring this out. And yeah, goodbye.